Good afternoon, ladies and gentlemen. My name is Ryan. I will be your conference operator for today. At this time, I would like to welcome everyone to the Emission Benefit of Energy Efficiency and Renewable conference call. All lines have been placed on mute to prevent any background noise. Should you need any assistance during the call, simply press star, then the number 0 on your telephone keypad, and an operator will come back to you to assist. It is my pleasure to turn the call over now to Ms. Denise Mulholland. You may now begin the conference, ma'am.
Thank you so much. Good afternoon, everyone, and welcome to the webinar. My name is Denise Mulholland, and I'm with the U.S. Environmental Protection Agency's State and Local Energy and Environment Program. Our program works to support state, local, and tribal governments who are designing, analyzing, and implementing programs that reduce the environmental impacts of their energy use. We know that many of you are thinking about how to quantify the energy and emissions benefits of energy efficiency and renewable energy, and we're hoping today's webinar will help inform your efforts going forward. Before we get started, I'd like to turn it over to Alexis St. Juliana, who's going to give us some information on how you can participate in the webinar today. Alexis?
Yeah, thank you, Denise, and thank you, everyone, for joining today. I'm going to go over some quick housekeeping items. The first is that there are 2 options to listen to today's webinar. The first is through your computer. Just please make sure your speakers or headphones are unmuted. The second option is to call into the phone number that is on the screen right now. You may need to mute your computer speakers if you use that option. All participants, whether they're connected via the phone or computer audio, will be muted throughout the duration of the webinar. There are 3 different ways to participate today. The first is that you can enter questions into the Q&A box on the right side of your screen. If you could, please let us know who your question is for, and we'll moderate all the questions at the end of today's webinar. Any questions that we don't have time to answer, we will post to the EPA website after the fact. And one other thing to note about today's webinar software is that all hyperlinks that you see on your screen are active. So if you see a hyperlink and it's something that you would like to explore, go ahead and click that link and follow it to the web page. The second way to participate today is through polling questions. It should be fairly simple to participate, but if you happen to be on a mobile device or tablet, you may need to exit out of full screen mode and tap on the poll icon, which looks like a small slip of paper dropping into a ballot box. And then the third and final way to participate today is by completing our webinar feedback form. You should be able to see the link to that in our Q&A box, and we'll also post it at the end of today's webinar. That's all I have, Denise.
Okay, great. Thanks, Alexis. Okay, well, now that you all know a little bit of background about me and our program, and you've now heard how you can participate in the webinar, we wanted to start with a poll to learn a little bit about your experience estimating energy and emissions benefits from energy efficiency and renewable energy. So we're going to pull up a poll question that should be coming to your screen. And essentially, we're looking to find out, are you new to this type of analysis? Have you estimated just energy benefits before? Maybe you've estimated just emissions benefits. Maybe you're familiar with estimating both energy and emissions benefits. So if you could just take a few seconds and answer our poll, it'll just give us a sense of everybody's level of experience. Okay, so it looks like we have a good split of a lot of folks that are new to this type of analysis, and then some that are, familiar with it. So this is a nice range of folks to have on the call, and we're hoping that we can increase everyone's knowledge about quantification a bit this afternoon. So the way that we're going to work from here is that I'm going to start the presentations today by giving an overview of a resource that EPA recently updated called Quantifying the Multiple Benefits of Energy Efficiency and Renewable Energy, a guide for state and local governments. You can use this guide to learn more about different methods and tools that you can use to quantify energy and emission benefits. And speakers after that will be talking about those methods and tools. We do have a great lineup of analysts that are going to talk about their own experience quantifying energy and emissions benefits from energy efficiency and renewable energy, and they're going to be describing, they've used a range of basic to sophisticated methods and tools that are also described in the multiple benefits guide that I'm going to talk about first. So without further delay, I'm just going to jump right into the overview and give you information about the multiple benefits guide. this is just some information about the program that I told you that I work for. Essentially, we work with state, local, and tribal governments, and we provide tools and information resources to help them, among other things, quantify the impacts of their energy efficiency and renewable energy strategies that they're considering. The research that I want to talk to you about today is will give you a lot of information about methods, tools, and data sources that you can use to do your own analyses of emissions benefits from energy efficiency and renewable energy. The guide is divided into two parts. The first part really talks about sort of what, why, and when you would quantify the multiple benefits of energy efficiency and renewable energy. And then the second part really gives you information about how to quantify them, so the different methods, tools, and steps that you can use to quantify the benefits. Our goal is really to make it easier for you to understand the process and to help you compare across different methods and tools and choose the appropriate ones for your purposes. So I'm going to dig in a little bit about each of these areas of the guide. So in the first part, we talk about, what are the benefits of energy efficiency and renewable energy. So essentially, you have electricity generation is reduced through energy efficiency, and you increase the generation of renewable energy resources. That can lead to reductions in emissions, which can improve public health. It can also enhance the electricity system, which reduces the cost of electricity service and avoids the need to build new transmission and power generation sources. It can also boost the economy by creating jobs and saving money. And so collectively, energy efficiency and renewable energy can generate great benefits to society, and we talk about that in the guide. And then we also talk about, when and why would you quantify multiple benefits. So there are essentially 2 points that we'll talk about. When you're designing policy options, you're considering a whole, list of different programs that you might implement. That's a good time to really stop and think about what are the potential impacts of these options that I'm considering, and how much do they, how much will they bring me closer to the goals that I'm trying to achieve? What kind of benefits will they deliver for us? And then it's good to go back after you've evaluated policies and programs, or after you've implemented them, to evaluate the impacts. Did they meet your goals? Did they get you what you were looking to achieve? And if not, maybe you need to modify the design of the policies or programs. So once you get to part 2 of the guide, it really talks about how you can quantify multiple benefits. And so from here you have, with any analysis, you have key considerations. So you're going to identify the purpose, the priorities, and the constraints that you have for your analysis. It's important for you to understand the different types of methods that you have available to you, and I'll talk a little bit about that in a few minutes. And then it's important up front to map out the strategy for the analysis. From there, you quantify the direct electricity impacts. That's really the foundation for any subsequent benefits analysis, is figuring out what are the electricity impacts that you're going to then use to quantify the electricity system benefits, the emissions and health benefits, or the economic benefits. And together you can use that benefits information to support informed decision making. So what we have today is we're going to be, here's first, as part of choosing a method for quantifying the impacts, there's some considerations that you'll think about. And those include, what benefits do you care about? For example, in this call, we're talking about emissions benefits. What level of rigor is needed? Is it a screening level analysis or a more rigorous regulatory impact analysis? What is the time period of the analysis? Is it short-term or is it a long-term type of analysis? What kind of data do you need? What kind of data do you have? What are the financial costs or technical expertise required of a particular method? And what resources do you have available for it? So these are all things that you'd have to consider regardless of what analysis you're planning. But you can then use the guide to map out the different benefits that you're going to quantify and then look at the methods that are available for you. So this schematic right here just depicts the different chapters in the multiple benefits guide and shows you how, starting with direct electricity impacts at the top, you can quantify either electricity system benefits, the emissions and health benefits, or economic benefits. And today we're going to be focusing on these top 2 boxes, really, or the top box, electricity benefits and the emissions benefits. In each chapter, you'll find step-by-step instructions, as well as a range of basic to sophisticated approaches that you can use. We have key considerations that give you tips on what to do as you're planning and conducting your analysis. as well as case studies and lists of tools and resources that are available for your purposes. So here's just an example of something coming from the chapter on estimating direct electricity impacts. You have options when you're at this point of an analysis. You can either adapt existing studies that others have done for similar programs, for different energy efficiency or renewable energy programs, maybe in a neighboring state, and you can just adapt it to your own conditions or your own assumptions. You can also use data from energy efficiency or renewable energy potential studies to sort of set some targets and some goals for what you'd like to achieve through your policy or program, or you can conduct your own new analysis using different methods and tools that are available. And essentially, there's a range of assumptions that you would need to consider, and you can find more of them in the guide. But for example, it's the program period. How long will this program be in effect? What is the target of the program? What is the anticipated compliance or penetration rate? So basically, how many people do you think you're going to reach through your program? How long are the savings going to last? This is particularly important for energy efficiency. These are things that you need to be thinking about, and the guide describes these assumptions that you need to consider with information about specific ways that you can think about it. Transmission and distribution loss, there are things that you can calculate into your estimates that you want to take into account. And also other assumptions like funding and program administration. How is your program going to be funded, and does that take away from the amount of money that you might actually put towards the program? So there's a variety of considerations that would go into your estimation of direct electricity impacts, and you can learn more about those in the guide in Chapter 2. When you get to the point of looking at your methods, you want to compare across the different emissions quantification methods that are available. And essentially, we have, throughout the different chapters, but certainly in the emissions quantification chapter, a range of basic to sophisticated methods that you can choose. And so basic include methods that are relatively simple, static approaches or factors that you might multiply by your electricity savings. An example of that is eGrid that Jeff and will be talking about soon after me. An intermediate approach is a bit more dynamic and has a bit more greater level of detail. It gives you a bit more information about the types of impacts that you're going to get from your energy efficiency or renewable energy investment. And an example of that is EPA's AVERT model, which you'll hear Eric Shrago talk about his use of that in a little bit after me. And then at the other end of the spectrum is sophisticated modeling, which is more dynamic, more complex, can be used for shorter long-term analysis. And an example of that is Juicebox, which David Abel will be speaking about his experience using that sometime during today's webinar. So there's a range of approaches that you can choose, and there's lots of tables in the guide that can help you compare across the different methods in more detail and tell you what the strengths are, limitations, when you might use them, and examples. There are also lots of flow charts and figures that can help you navigate the process and figure out, in a stepwise fashion, what do you need to do given the approach that you've chosen. And there are a lot of case studies that you can look to see how others have quantified similar types of policies and programs through their analysis. And finally, there's information about available tools and data resources that you can use for each chapter and for each step of the process that we described for you. So with that, there's a link to the guide right here that I think you can link to, and we'll be posting the slides. You can certainly find it here or by Googling it or looking on our website. But essentially, I hope that you can look to this resource as something that can guide you in your efforts to quantify electricity and emissions benefits of energy efficiency and renewable energy. So thank you very much for your time. I think what we have at this point now is another poll. So we have a second poll, and this poll is just going to help us know a little bit more going forward what you'd like to learn about. So the question here is, what information on approaches for estimating energy and emissions benefits would you most like to learn? So I talked about screening level and intermediate level and advanced approaches for estimating energy or emissions benefits. And you can choose as many as you like, I think, for this one. But select which ones that you'd be interested in learning more about, and that can help shape future webinars as well as future materials that we develop for our audience, for you. So it looks like so far the biggest interest is in intermediate level approaches. So, okay, so we're looking at both intermediate for both energy and emissions benefits. Okay, well, great. Well, thank you very much. That's really helpful. And we'll use that information going forward. So at this time, we're ready to move on to our next set of speakers and sort of begin the part where the analysts will talk to you about their experiences. So in the first presentation, we have Dr. Jeffrey Haberl, who is a professor of architecture and associate department head for research in the Department of Architecture at Texas A&M University. His work emphasizes building energy modeling, statistical modeling, and many other things, but particularly procedures for calculating air pollution savings from energy efficiency and renewable energy projects. He is also the co-principal investigator of the laboratory's Texas Emissions Reduction Program, which he'll be talking about. His associate, Dr. Juan Baltazar, is an associate research engineer. His area of expertise is in renewable energy systems and energy use efficiency. He's got extensive knowledge of solar thermal systems and over 25 years of academic research in these fields, and he's developed his own software programs for energy analysis and simulation. So they're going to speak to us today about their efforts to quantify nitrogen dioxide emission reductions from energy efficiency and renewable energy in Texas, including through the use of one of the basic methods that I mentioned earlier, eGrid. So with that, I will turn it over to Jeff and Juan Carlos.
Okay, well, good morning, everyone.
Good morning.
We're going to take a few minutes and give you some idea of what we've been doing here in Texas. Just a couple of things. I'm no longer associate department head, and Dr. Baltazar is actually a professor in architecture, so I see we've got some web page maintenance to do right there. I'd like to talk today about a project that we've been working on in Texas now for a number of years, since 2001, the Texas Emissions Reductions Program. And as part of that, I need to acknowledge a lot of input from our staff and students here. The co-PIs on the TERP program is myself, Dr. Baltazar, and Mr. Bama Yazdani, and we perform various different aspects of the work. In addition, we have a number of staff and students. This is an example of some of the people associated with it. I'm on the left there, Bauman's the next to the left, and Professor Baltazar is next to him. We also have Gally Silberstein, we have Shirley Ellis, Patrick Parker, and Angela Rao on our team. And we are privileged to have a number of very talented students that help us out with the work as well. Shown there is Minjae Shin, who's now associate professor at the University of Alabama, Farjad Kiri and Kimbo Lee, who both just received ASHRAE scholarships recently, Sung Kyung Jung and Chul Kim, who've been working with us currently on our program. So this is a privilege to really present the results of a number of people that are working on the program. So I've really tried to summarize some of the information up front so that you can get a sense of what I'm going to be presenting. So a couple of the questions that we were asked is, what policy or program are we analyzing? So if you've heard, we're analyzing the Texas Emissions Reductions Program. This is funded by the Texas State Legislature, which means, of course, we report annually to the TCEQ. So everything I'm talking about today is online on our lab's website. If any of you have trouble sleeping at night, I would strongly recommend you download the reports, and they'll put you to sleep in a jiffy. The benefits included and why, well, NOx emissions reductions is important in Texas. We have ozone problems in a number of our large metropolitan areas, and so reducing the oxides of nitrogen is important for clean air in Texas. Our results are used by the Texas Commission on Environmental Quality, TCEQ, for weight of evidence and the Texas State Implementation Plan. Similarly, as part of our program, we tried to have outreach, so we've developed a number of conferences for that. Our annual conferences so far have been the Clean Air Through Energy Efficiency, the CAEDE conference, which we've now relabeled as the Texas Energy Summit to be a little more broad-based. We've also developed a number of online web-based tools, International Code Compliance Calculator for calculating emissions reductions from building codes, and our NOx emissions calculator, which we're in the process of retooling and will have available shortly. Similarly, we were asked, how do we quantify the benefits within the state here? In general, we quantify each year's benefits as we go forward. We've been doing this since 2001, and we use the method for actually weather normalizing these savings back to the base year. So depending upon which entity we're measuring, we use change point linear models for weather normalizing things such as wind energy savings. We use sliding averages on some of the data to give us some idea of how some of the wind farms are producing lately. And then we have special purpose models for things like solar PV and solar thermal analysis that were developed by the University of Wisconsin. The data sources that we get our data from are the participating state agencies, the State Energy Conservation Office, SECO, Public Utilities Commission, TCEQ, and then the ERCOT, who provides a lot of the electricity data that we use for our basic analysis. We also rely on data from 4 federal agencies. The EPA provides us with eGrid. National Renewable Energy Laboratory tracks a lot of the installations of renewables. And NOAA provides us with the weather data and the Energy Information Administration as well. So we're having to reach out to a number of agencies, and then we turn around and provide results to a number of different agencies. All of this is done very closely in collaboration with the TCEQ, and of course we do have a lot of oversight and cooperation with the EPA for our data quality and our annual reporting. So our work was legislated within Texas. Back in 2001, we were faced with a very strong mandate to improve the air quality within the state. So our original legislation was set forth to enable this work. I'm not going to go through this in detail, but you can see through the years it's been added and modified clear up until the current time, where we have a number of specific responsibilities that the lab has to produce as part of our funding from the legislation. Part of that is the actual calculations of the emissions reductions. Our credit for the emissions reductions follows the EPA criteria for SIP credits, which have 4 primary elements. First of all, the emissions reductions need to be quantifiable. So we have to provide a method for quantifying the emissions reductions. We need to review that method with TCEQ and EPA, and then we use that method year after year to quantify the emissions. That method needs to make sure that it doesn't account for savings that are already accounted for somewhere else. So we have to be careful of any surplus accounting and abide by that accordingly. We also have measures that need to be enforceable. For example, building codes are enforceable. When you install a wind turbine, it's something that actually exists. It's not a hypothetical thing. Similarly, we have to perform the record keeping. So if somebody wants to go back and look at the savings in 2013 or 2015 or 2006, all of that is kept online in the format that's required by the TCEQ. This is an example of one of the online reports. As I said, this is part of a larger program that does emissions reductions from not only renewable energy, but also energy efficiency. So there's a number of areas that we do the emissions reductions on that I won't be talking about today. However, we do have information available on our website about that. So for example, single-family construction, multifamily, commercial construction, and this is construction to code or above code programs. Likewise, green power production, I'll be talking about that today. We also take information from the public utilities programs, energy efficiency efforts, and incorporate that into the emissions reductions. Energy efficiency programs that are managed by the State Energy Conservation Office. And one item here, and we've had additional items from time to time that we're tracking, is the air conditioner improvements as people retrofit their houses and commercial buildings around the state. So today I'm going to be talking about the savings from renewables. So primarily we'll be talking about savings from installations of photovoltaic, both on residential, commercial, and utility scale, solar thermal installations, hydroelectric, biomass, landfill gas, and geothermal installations. However, the big ticket item, as we'll see from some of the results coming up, is the emissions reductions from the wind farms that have been installed around the state since about 2004, 2005. So we'll start with that, looking at the wind farms that have been completed. One of the procedures that we have to do is to carefully map out where those farms are, and then we have to know how those are connected to the grid, so the accounting is done appropriately with eGrid. So on this graph, for example, we're showing you where the farms are installed around the state. This is a graph of the completed farms. We also track announced and retired farms. This is as of December 2017. So you can see, for example, they're primarily in the western part of the state, as well as the Panhandle, and now a little bit more in the southern part of the state. But all of those are where we are tracking our wind farms, and we basically get the actual data, the 15-minute data from ERCOT for each of those wind farms, the Electric Reliability Council of Texas. This gives you some idea of the success of that program. Beginning a little bit before September 2005, we had less than about 1,000, 2,500 megawatts of installed wind capacity. We're now exceeding about 20,000 megawatts, probably 21,000 as I speak. So not only do we look at the installed capacity, we also track the production of the wind from these wind farms. And as you can expect from your own common experience, the wind doesn't blow all the time. And it blows more in some parts of the year than it does in other parts of the year. So that's one of the issues about weather normalizing and then calculating emissions reductions from wind. So this graph with the shaded bars going down the graph shows you the years that we've been tracking the wind farm electricity production. Excuse me. And you can see the dog days of summer, which are the shaded bars, are the periods when we tend to have the lowest consumption of wind. Those are usually during the summer period. Unfortunately, when the electricity requirements are the highest. So there is a bit of a seasonality to the wind within the state. We developed a procedure for that. This is one of several flow charts we use, but I think it's probably easier to think about that in this format. Okay, so we basically have energy efficiency categories, residential, commercial, industrial users, and we have wind, solar power, and eventually tidal power at some point, renewable energy categories, and then we have our transmission and distribution substations. So the trick really is finding out where these facilities are, linking them with the appropriate crossover back to the power plants. We use eGrid for that, and then running the calculations. So for example, I'm reporting today on renewable energy, which is the lower right-hand box. We also track energy efficiency projects. So we're looking at all of those. Where is the energy being consumed? Is the project something that's enforceable? Do we have record keeping on it, et cetera, all the EPA requirements, and then tracking that back to the source. So to do that, of course, we then link it back to which of the power plants during the previous years which are actually producing the electricity use, and what would that reduction in energy be. So if we look at wind energy, for example, one of the early sites where we try to prototype this was a research facility up in Randall, Texas, and we had a Intertech wind turbine. And so we looked at the data coming off of that wind turbine, and we said, there's a pattern to that data, and you can see that here, for example. The upper orange dots are basically the power coming off the turbine plotted against NOAA wind data. And of course the blue dots, which are much better defined, is the same wind power coming off the turbine plotted against on-site wind measurements. And of course, one of the problems with that is that it is more applicable to use the NOAA wind data than it is the on-site wind data. So we shifted to the on-site wind data, to the NOAA wind data. We developed daily regressions, change point linear regressions, which give us the average daily wind savings. And we use that to do the forecasting. So in this case, we're actually able to take 2017 data, backcast it to the 2008 base year. We've done this now across all the wind farms in the state, so that looks something like this when you add all those up. and that gives us the total savings for the wind farms. Here's another example from one of those wind farms, the Callahan wind farm. Here's the actual hourly data. There's the daily average data during the ozone season period, non-ozone season period. And there's what it looks like when you've been tracking data now for 10 to 15 years. You can begin to start answering questions about how reliable is that data. We know exactly where the power plants are in the state thanks to eGrid, and so we're able to track that and then take it back to the power plants that would have provided the power during the periods that wind were blowing. In Texas, we have 4 congestion management zones that are shown there, and that's how we divide things up around the state. The results that we've seen here for the wind energy production, for example, in their last year, it was about 122,000 megawatt hours on ozone season day. The actual NOx emissions reductions were about 65 tons of NOx on an ozone season day. You can see a dramatic jump between 2016 and 2017, and that was basically a resetting of the numbers within the eGrid. So this goes forward then for all the renewable energy projects. We have a process like that. We roll it up into a final number, which is something that looks like this. The green bar, of course, is the total energy consumption. The other colors are the PV, solar thermal. That allows us then to account for the renewable energies. We wrap that together with the energy efficiency projects across all the agencies, which gives us the roll-up for the total value for the state. This is what that looks like across all the projects. And, of course, the results of the analysis we report to the legislature. The outcomes have provided Texas with NOx creditable emissions that can be used in the weight of evidence. The challenges, of course, are gathering all this data, coordinating across state agencies, and then doing this over a 17-year period. Questions?
Well, thanks so much, Dr. Haberl. That was really a very informative presentation, and we're going to actually save questions for the end, and I believe you might be ducking out, so I believe Dr. Baltazar will be available to answer any questions on this presentation at the end after our last speaker has gone. So thank you very much for that very informative presentation.
Thank you.
Great. So now I'm going to move on to the next presenter, which is Eric Shrago from the Connecticut Green Bank. And at the bank, Eric is responsible for the general management of the operations there. And this includes the organization's strategic planning, impact assessment, as well as the evaluation, measurement, and verification efforts that they have underway. He's also responsible for administration, human resources, and technology functions. So he's got a lot on his plate there. Eric is going to speak to us today about the Connecticut Green Bank's efforts to quantify the emissions benefits of their investments. And he'll be talking about the use of an intermediate tool that I mentioned earlier called a VERT. With that, Eric, take it away.
Awesome. Thank you. So I'm from the Connecticut Green Bank, and I'm going to talk about how we've employed a VERT overall in the organization, and then specifically how we used it most recently with on a recent transaction. So this is the Connecticut Green Bank securitization of solar home renewable energy credits and their emissions benefits. So Connecticut Green Bank, we're quasi-public in the state of Connecticut with a mission to increase investment in clean energy in the state. So that's renewables and energy efficiency and help to reduce the energy burden overall in the state. We were launched in 2011 in our current form, basically using finance to do that. And since then, we have mobilized over $1.3 billion of investment into the Connecticut clean energy economy. We've created 16,000 job years, reduced energy burden for 30,000 homes and businesses, and deployed more than 285 megawatts of clean renewable energy. And I go through those numbers primarily because it's really important on how do we get to those. And I'll come back to all of how we get to that, but I want to just pause and first talk about the solar home renewable energy credits that we have earned. So overall, we have a program here administered by the Green Bank, the Residential Solar Investment Program. or RSIP. And RSIP is a declining block incentive targeted at homeowners to install solar on the roofs. It has a 300 megawatt cap. And basically we had some limits on how much of our funding that we could direct towards RSIP. However, we're seeing a lot of people trying to get through the gates of the program a lot quicker. And so effectively, we lent ourselves money to pay for that from one side of our business to the other. And so we continue to pay the incentives. We administered the program. The issue was we needed some way to cost recover that. The legislature stepped in 2015 and allowed us, or created a special class of renewable energy credits linked to the solar from these systems, and gave the Green Bank the right to retain those RECs and monetize those through long-term purchase contracts with the state's two investor-owned utilities and counting towards their renewable portfolio standard. So ultimately, the way this works is a homeowner will install solar, they generate credits, the Green Bank gets those, registers those, aggregates those, and then sells those to the utility at a prefixed price, intended to recover the cost of the program. And we worked with the legislature to design this basically with the intent that we would securitize these streams of income down the road through some sort of green bond. Our budget took a hit a couple of years ago, and some of our funding was diverted. And so our need to monetize these credits in bulk fashion and securitize those really came to a head. So we went out to the capital markets about this time last year with this transaction for 2 years worth of these Shrags. And we started working to sell those. And so through that process, we started getting some feedback that investors really didn't just want something to be certified in terms of a transaction. They wanted to know what the impact was. And so we thought, this is a great opportunity for us to showcase to impact investors what we're actually achieving through this and what they can achieve by joining in on our transaction. So this is all just overview of what we did for the Shrek transaction. So this ultimately ended up being about $38.6 million we took to market. So what is the actual impact of the Shrek bond? What's the impact that the investors in this would have? And so we wanted to model that. So we, at the Connecticut Green Bank, have some pre-established methodologies across the organization. And so we didn't just want to use those, we wanted an outside opinion. So first we went and said, all right, let's make sure that we get this rated by an outside verifier. So we engaged with, through an RFP process, we engaged through Kestrel verifiers to assess the bond. They did a certification, and we have filed our paperwork. We're still awaiting the official stamp, but we have no reason to believe it won't be certified as a climate bond per the Climate Bonds Initiative standards. But we also, as I said, we really wanted to get that impact quantified. And we wanted there to be some sort of outside methodology to that in terms of things that would be trusted by the market. So we wanted to say, what did these achieve? What were the greenhouse gases that were avoided? How much cleaner is the air? What were the public health impacts? And what were the economic impacts? So we engaged with the Climate Action Reserve to do that. And just as the Green Bank, as I was saying a minute ago, we have our overall framework of evaluation. So we have a bunch of different methodologies that we can use. And here I'm going to focus on our environmental methodologies, obviously. So we have employed AVERT, I think about 2 years ago, as our new official methodology for estimating the impact of air quality improvements due to our activities. And we did that, initially we were doing this when we were looking at larger projects to say, okay, if we finance this this wind farm this is what we can expect the large impact to be. However, the vast majority of our projects, especially in the RSIP program, are small one-house rooftop solar projects or an aggregation thereof. And so we really needed a way to operationalize this because we couldn't sit there and run each project through a VERT. So through a regression analysis, we developed some factors that work in the state of Connecticut that take the type of project that it is, if it's energy efficiency or solar, using the standard built-in assumptions of a VERT and translate that into factors for NOx, SOx, CO2, and particulate matter. So we built that in. We've automated that through our data warehouse, and with respect to the Shrek Fund and every other program that we had, we were able to create some estimates. And so when we were looking at this Shrek offering, we had, hey, look, the energy impact is this is 109 megawatts of installed capacity. It's going to generate 123,000 and change megawatt hours. That's over 3 million megawatt hours expected lifetime generation using our jobs methodology. That represents $39.7 million in pre-make advancement, leading $384 million in private investment, creating 5,600 jobs through our jobs methodology. And from an environmental impact, we said, all right, running using our methodology and how we do that, we were getting this reduced emissions by 69,000 tons of CO2, 71,000 pounds of NOx, 58,000 pounds of SOx, 6,000 pounds of particulate matter annually. But again, we wanted that independence, so we engaged CAR. And they put together a report, and they said, okay, here you go, and your savings is, in terms of air quality, is 749,500 CO2 over the lifetime of this project, which we said, going back to our estimates, well, we're expecting a lifetime savings of 1.8 million. Why is there a difference? Is this something to do with methodology? So we had a long discussion with CAR after we were starting to second guess ourselves, and they take this one step further, where they use EIA estimates of the grid and how that is expected to change over the useful life of the project. We run this scenario through a VERT based off of a changing grid and projecting out future years. So they're actually assuming a grid that's cleaner on its own without these projects in there, whereas we're assuming that just keeping the baseline year for these projects static. So that really explained the difference and has caused us to think of how do we want to adapt our own internal processes going forward in terms of do we want to account for changing grid composition, or are we happy with the way that things are? And it also made us look back at how are we using our forecasts. We had built ours off of a mix of P50 and P90 forecasts, which we've adjusted for. And we're also going to go back and integrate our where we have actual generation numbers so that we can see what that actual impact was in terms of air quality on the grid. And we have built a platform in conjunction with Locus, who's an EM&D monitoring vendor in the solar space. And so we have real-time generation numbers that we're able to run that through a VERT and say, this is what we're seeing as the savings. So ultimately, we were able to pitch to investors what these impacts were, and our bonds sold for $38.6 million on April 2nd. And so the buyers know what their investments have now achieved. And so for questions, feel free to reach out.
a really interesting presentation, and I'm sure we'll get a lot of questions about what you did and what you did for it. It's a very exciting effort, and I know I've enjoyed watching you and working with you on it as well. So, so thank you very much for that presentation. So at this point, then, I'd like to turn it over to David Abel, who's going to be our next presenter. David Abel is working on his PhD, or has his PhD from Environment and Resources, Energy Analysis and Policy. He's based at the University of Wisconsin-Madison, and he focuses on policy-relevant analysis of energy systems, air pollution, as well as public health. He explores the intersection between energy and the atmosphere, namely the impacts of energy technologies, trends, and behaviors on air quality, climate, and public health. And David is going to talk to us today about his experience quantifying emissions impacts using at least one more sophisticated tool that he'll talk about. It's called JuiceBox, and a bit of AVERT, too. I think he's going to tell us about his experience there. So with that, I will turn it over to you, David. Thanks so much.
Yeah, thanks, Denise. So, yeah, again, I'm David Abel. I'm from the University of Wisconsin-Madison. I'm a postdoc, actually, now in the Holloway group within the Nelson Institute for Environmental Studies. And if you couldn't tell from my introduction, this topic is really near and dear to my heart. It's what I spent the last 5 or 6 years of my life working on. And I've used all of these different methods that are being talked about today, from eGrid to AVERT. And today I'll focus on a couple examples of sophisticated methods that we've used. So of course, first, an obligatory slide. Thank you to all of our support and my different collaborators. Special thanks to my PhD advisor, Tracy Holloway. And also special thanks to a couple names down there, Paul Meyer of Meyer Engineering Research. He actually created the JuiceBox model that I'll be talking about. And thanks to some University of Wisconsin funding sources, as well as the NASA Health and Air Quality Applied Sciences team. And so I like to put this slide up at the beginning of every talk I give just to orient the fact that I really think this is, we often get deep into a single topic, but this entire discussion that we're talking about in this webinar today really has to do with a whole sphere, and that changing anything in any one of these little bubbles in climate or on public health or in air quality really affects and reverberates through all of the others. And so the motivating questions behind what I'm going to talk about today and why sophisticated tools were especially good for the couple of examples that I'm going to give are one, just the general scientific research question of, can we improve understanding of interactions between energy, air, climate, and health? And then the big why behind that is, can we identify and quantify some win-win solutions across these different bubbles and across these different topics that are cost-effective and really benefit everybody? And so just to start and make sure we're all on the same page with some of this, I'm going to be talking about emissions, and when I'm talking about emissions, what I mean is emissions from power plants. And really predominantly two different pollutants, sulfur dioxide, SO2, and nitrogen oxides, or NOx. And the reason these are what I'm talking about is because what we really care about and what we regulate in the U.S., at least as far as criteria pollutants go, are ambient concentrations in the atmosphere. And the two pollutants that are really public enemy number 1 and number 2 for public health are fine particulate matter, PM2.5, and ozone. And SO2 and NOx both contribute to PM2.5 and ozone in the atmosphere. And then one last, of course, we can't forget about CO2 as a greenhouse gas. We care about it for a slightly different reason, but it's very interrelated with all of this work. And then why do we care? Why are there air quality regulations to begin with? Why is anybody like me doing research? Why is anybody funding this type of work? And really it comes down to the fact that this is a big public health benefit to control and manage our air quality in the U.S. And globally. So in the U.S. we spend about $50 billion a year under the Clean Air Act to achieve standards. And the reason why we do that, of course, is because it has huge benefits. And we've shown that there are about 30-to-1 returns in health benefits from that $50 billion that's spent every year. And I'll show I've got these pictures here showing between 2005 and 2016. This is actually just concentrations of NOx pulled from a satellite an instrument called the Ozone Monitoring Instrument. And you can see the drastic improvement we've had in air quality over just the last 11 years, or 13 years now. And so this 100,000 deaths a year in the U.S. is really to make the point that even though air quality has been a big environmental success story in the U.S., that's still the number that we're working with, and that's still a big number of deaths and big impact from air quality that we have to address. And of course, if we zoom outside the U.S., the work that I'm talking about and most of what I have done focuses on the U.S., but if we zoom out, it's a much bigger problem. And I think the number that really epitomizes that is that 91% of the global population is exposed and lives in a region with pollution above what the World Health Organization deems as safe. And so I took this nice picture. This is actually from the AVERT website. So it's built around why should we use AVERT, and the big reason there, we've just heard what can be done with it, and it's a nice intermediate method between a grid and e-grid and some of these sophisticated methods. I said earlier, I've used all of these different methods, but what you can get with a sophisticated method that you really can't get with the basic and intermediate methods sometimes are this real simulation of how the grid works based on all of these different parameters and factors that build into every single power plant. So you have a model that actually simulates reality by taking in fuel prices and environmental regulations and emissions factors and different technologies, and combines all of that to then calculate, in this case, dispatch, and which power plant is going to produce how much energy and how many emissions and when. So the first thing I want to talk about is actually sort of related to the benefits of energy efficiency and renewables, but actually more of a warning. And it's the fact that this was a long-term project that we worked on for a long time through the National Institutes of Health. This recognition of this fact that as the climate warms, one of the first things that we're going to need to do to adapt to higher temperatures is to cool our buildings more and use more air conditioning demand. And that means that we're going to have to produce more energy from somewhere to power those air conditioners. You can draw this connection all the way from climate and weather through building energy demand, electricity production, power plant emissions, air quality, and then health. And that's what we did with a series of models. This work was published in a special issue of Pulse Medicine last summer on climate change and health, covered by The Economist. It was a highlight in Nature Climate Change. And the way to think about this study is, I'm going to kind of go through this fast so I can talk about two different things. The way to look at this study is really just through three different scenarios, one being present day, current reality, and then two future climate scenarios, looking at what would be the impact of a warmer climate alone, and then this mid-century adaptation scenario. The third one is what would be the impact of climate plus the added emissions from increased air conditioning use. And we used a series of models starting with modeling the weather and the climate, future weather, then running a building sector model to estimate what energy demand in buildings actually would be, and then feeding that into the real big model that I want to talk about, MyPower, or JuiceBox, which calculates the electricity dispatch and inline emissions from each power plant, before then feeding into a chemical transport model that calculates the air pollution, and a health impacts model that then turns that into why do we care about that air pollution change. And so a couple key challenges with this work is, one, how do we link these interdisciplinary tools, and how do we manage interdisciplinary teams? And this is often a big issue with sophisticated energy models, because in many cases those models were not built specifically to do air quality research or even emissions work at all. Or if they do emissions work, sometimes they stop at CO2 and greenhouse gas emissions because they're a little bit easier to quantify. And so connecting all of these steps together is definitely non-trivial. So the first thing I'm showing here is just to make the case that yes, in a mid-century climate, the eastern U.S. is warmer. So in the present case, you can see there's actually a small decrease in minimum temperatures by the middle of the century, but there's a huge increase in the frequency of high temperatures across the eastern U.S. by the middle of the century, and greater variability overall, which this all fits within what we know about future climates. But what this allows us to do by having this scenario then is we built 39 different building prototypes that represent 85% of energy demand. And by feeding this new meteorology into that model to recalculate energy demand, we can then approximate what energy demand in the U.S. might look like in a future warmer climate. And once we have that information, then we can go to the real meat of this talk, right? The actual emissions quantification piece. So what we used is something called MyPower, or it was actually originally developed by Paul Meyer and Meyer Engineering Research as an educational tool. So if you look for it, it's much more commonly known as JuiceBox. And what this does is it was really meant to fill a gap actually between, we've got this whole category of sophisticated models, but it was really meant to fill a gap between AVERT and super, super sophisticated, difficult, market analytic type energy models that don't really or weren't really built to do emissions work. So this is built to actually do this inline emissions quantification, so we can provide it load shapes based on what came out of our building models, as well as lots of different data sets on the types of power plants that are out there and fuel costs and things like that. And it can calculate dispatch and emissions in line using what's called a load duration curve approach. And I can talk more about that if there are questions. But I'll move on from now to what we get out of that model. And what we get out that we care about for this type of work is the emissions. So here I'm showing histograms just like the temperature of SO2 and NOx emissions. And there's slightly different behavior here than what we saw for the temperature. And I think the biggest thing here is that there's not really an increase in the maximum number of emissions at any given time over, this is 1 month in the summer. But there is an increase in minimum emissions, and there's a much greater frequency of emissions in this upper 50% of the range that we might see from power plants. And the reason this occurs is because what we see in the future climate is not really a dirtier mix of power plants overall, but that the dirtiest mix of power plants has to run more often to meet these times of higher demand with greater air conditioning. And then I'm going to jump through these key findings pretty quickly because there's actually another webinar in the middle of May where I'll talk more about some air quality and health takeaways from this type of research. But what we found was about 16,500 deaths related to PM2.5 and ozone exposure annually in a future climate. This fits within what some other work has looked at by just examining climate's impact on air quality. But the real new piece here is that about 1,000 of those deaths, or 5 to 8% for PM2.5 and ozone, are due specifically to increased air conditioning use or adaptation. And so why that's really important is because that's something we can control, right? And the natural question then is how do we address or manage how we use and produce our electricity so that we can minimize air pollution damages. And the key takeaway for people in a planning or policy position is really the fact that as long as we continue to rely on fossil fuels, and especially coal, to provide electricity, then using air conditioning to adapt to warmer climates is important and protects us from heat-related damages. But by doing that, we're just substituting heat-related damages for air pollution-related outcomes until we can create a cleaner electricity grid. And so, then the other natural question is how do we address this and manage it from the production side? And of course, one obvious solution is more renewables. So we decided to take a look at solar energy for managing air quality. What would happen if we got to high levels of penetration of solar throughout the eastern U.S.? And the way we approach this actually uses a second, more sophisticated model that was used in analysis over at the National Renewable Energy Lab. They did a series of studies and work through the Sunshot Initiative to look at barriers and opportunities to getting to high levels of solar across the U.S. And we took a scenario that they ran through this grid view model that was about 20% solar throughout the U.S. And what are the barriers and challenges to doing that? And why I really wanted to talk about the grid view model is because it really gets at the fact that not all of these models were developed to do air quality research. And this model certainly was not. It's a very sophisticated model, but it's meant for more market and economic objectives. And it builds in a lot of detailed representation of the transmission grid and market scenarios and transmission markets and all kinds of different things. Along those lines, I'm happy to talk about that more afterward if we want, but I'll keep moving so I can get through everything now. But what it does not do is it does not calculate emissions. So we had to then, to get the value of that sophisticated model and the sophisticated work that NREL had done in their work, we had to then come up with a way to estimate emissions. And what we ended up doing was to take our two different scenarios, so one being this base reality case, and the second being the high penetration solar case, which over the eastern U.S. ended up being about 17% solar by generation. And to just scale emissions from EPA's National Emissions Inventory by the change in generation at each power plant at every hour. So it's kind of a simple approach, but it's actually much more complicated in actually doing this. It involves first matching all the power plants from grid view with the power plants from the emissions inventory, and then taking this hourly data and actually doing the scaling and then capturing any extreme changes that might throw off the system. But at the end of the day, we get realistic results that show about a 17% decrease in traditional generations and mountain solar sources, gives us decreases in NOx emissions and SO2 emissions of 20% and 15% respectively. And one other thing that this study allowed us to do then was actually compare, because we only had one scenario of solar from grid view, we were able to compare a sophisticated tool like grid view with an intermediate tool like AVERT to then estimate the impacts at different levels of solar integration. So this plot is just showing the level of penetration of solar from 0 to 17% versus the change in emissions. And what we can see is that it's approximately linear, and AVERT does a very good job of capturing the SO2 emissions and a relatively good job of capturing the NOx emissions from grid view. And then the takeaways, what would we actually find, since it would be annoying to present a study and then not actually give any really good results. What we found was that 17% solar energy would reduce PM 2.5 in the eastern U.S. by about 5% on average, and as much as 10% in some regions. And this has health savings of about 1,400 lives saved annually, or $13 billion. And so to end, I'll say the answer to this real big research question of can we inform some of the in-between energy, air, climate, health of these bubbles, absolutely interdisciplinary models of varying complexity are all useful for analyzing this type of thing, from the eGrid, AVERT work, all the way through the sophisticated tools. And there are definitely cost-effective solutions for energy, air, climate, and health management all at once that exist. So thanks, and feel free to reach out to me with any questions now or after the talk.
Great, thanks so much, David. You did a really nice job of presenting, I think, complicated, what otherwise could have been very complicated material, or what was a complicated process, I'm sure, in a very understandable way. So, so thank you for that. So I think at this point, so we've received a bunch of questions, and we can go ahead and jump into the questions shortly. Please, if you have additional questions, type them in and send them, and we'll try and get to them in this call. But in the meanwhile, what I'd like to do is just do one more poll for the audience, and basically to just get a sense of your intent for how you would use estimated energy and emissions benefits from energy efficiency and renewable energy. So you can choose as many of these as apply. So essentially, you might be using it to provide information to policymakers, to provide information to the general public, for use in an energy efficiency cost effectiveness test, or to determine emission reductions for a state implementation plan. So please click on all the ones that would be relevant to what you might intend to do with these types of quantified benefits. So we'll give folks just a half minute or so. Okay. All right. So it looks like we have a lot of folks that are looking to inform policymakers, and certainly general public and cost-effectiveness testing are very popular. So that's really helpful to know, and certainly we'll keep that in mind as we're developing future webinars and resources. So thanks for that, folks. Okay, so then why don't we jump right into the questions? And so what I'll do is start with a question for Texas. I have a question on the Texas presentation. So Juan Carlos, I assume you're probably still with us and that Jeff might have moved on by now. But I have a question as to, is there a reason for the Texas analysis that eGrid was used instead of AVERT?
Yeah, basically, This is Jeff. I'm still here. Amazing.
Okay.
But we use eGrid because it's at the appropriate scale for the sorts of information we're gathering. We would love to use a more sophisticated model, but unfortunately the granularity of our inputs is not there yet.
But also, if I am allowed, it's also the power industry generation in Texas is very special. We are really in a cluster. We are not sharing much line. We have an ERCOT console that is taking care of all the dispatch in Texas. And with eGrid, we generate a particular model from the data that was generated to just for Texas. So allow us to manage very specific county by county what's happened with the generation. So it's a more detailed granularity that we could do that we could not find at the time with another tools.
Okay, great. Thank you. Okay, I have a question now that is directed to Eric. Eric, has Connecticut Green Bank done similar analysis for your geothermal heat pump program?
In terms of running it through a VERT, we have not. I'm curious to what geothermal heat pump program someone is talking to, because we don't have a dedicated program for geothermal yet. But similarly, as we do see, or the spread of heat pumps, this is something we would run through and develop a factor for that we could use for estimation of impact.
Okay, great. Thanks, Eric. Okay, so here's another question. This one is for you, David. I have an audience member who'd like to know, what is the difference between JuiceBox and the National Energy Modeling System, also known as NEMS?
Yeah, so there are a lot of differences. JuiceBox does take some data from NEMS, and I believe NEMS also uses this low duration curve structure, but there are a lot of differences other than that in basically every single way. And if we can touch base offline on more detail with that, and I can put you in touch with the person that developed JuiceBox as well. I suppose I should say, from the development, they're very different in that JuiceBox was meant to be an educational tool. So it's got a big user interface, and it's used in classes and things like that.
Okay, great. Thanks, David. Okay, I have a question for all three speakers, or four, depending on Texas. For all the speakers, how about that? Could you please describe give a general idea of the level of effort, so the number of staff, or how many months, that was needed to conduct an analysis projecting emissions benefits from energy efficiency or renewable energy to air quality ambient emissions? So basically, what's the level of effort, how many people, how much time, maybe even other resources, money, basically what did it take to do this type of analysis? So we'll start with Texas. Do you want to go first?
Yeah. Originally, we were budgeted at about 1.1 to 1.2 million a year for this work. Legislature some time ago cut the budget in half. Has never really restored it. So we've had to live on fumes for a while here. But we're currently running at about 600,000 a year, and that covers a large portion of the people mentioned on the overhead slide.
And that's also because Texas, we do a lot of the include several other energy efficient measures, not just renewables, and we do also sophisticated models for simulation in the buildings to the residential level or to the commercial level. It's a lot of the information that we presented here was simplified, but there is a lot of also sophisticated modeling that we did from the energy perspective.
So, for example, we provide a web-based code compliance calculator for residential, and we're in the process of developing one for commercial. That's part of the mix.
Yep, and it's still active in that time, and it has to be maintained.
So now, I appreciate, and before I move on to Eric and to David to answer as well, I guess it's sort of, let's step back maybe a little bit more generally, because I know Texas, you've had this program running for a really long time, and I know it's fumes for you, Jeff, but it's you know, it's well established. And so I guess if you were trying to think about somebody else that might be just starting out and and trying to figure out, you know, how many people would they need to do an analysis that would project emissions benefits from energy efficiency and renewable energy to air quality emissions, to air quality changes. You know, how many people and how much time should they plan for that?
You want me to answer that? Okay, a lot. You know, I mean, how important is clean air? It's plain and simple. It takes a long-term effort. It takes players that are going to be there for years and years. You know, all these things the EPA has put into their guidelines. Doing that really requires a significant amount of work. It also requires special expertise and you know, tremendous flexibility. You know, one year you're building up tools in one area, the next year you're building up tools in another. We're constantly evaluating available tools. The biggest problem we run up against, of course, is very few of the tools are open source. So we usually back down a little bit as soon as we hit a proprietary problem with that. We're currently working with several other states right now to begin to provide the types of calculations that we're doing. So, you know, we're happy to get other states up and running, and then turn it over to them and walk back to Texas, so to speak. And we're in the process of doing that. So it requires an equivalent amount of staff. Scale-wise, you know, if you have a lot of renewable energy installations, if you have a lot of energy efficiency going on, then you're going to have equivalent proportions to what we've been doing.
So this in our case is more because it's in a state program again.
Right.
It's a big program. For a project in particular, well, well-established models already exist, so it's very straightforward in some cases.
Thank you so much for that clarification. I think that's an important note, is that you know, it does depend upon the type of analysis that you're doing. If it's for a regulatory purpose, you might need to use more sophisticated models, which may require more sophisticated you know, staff with greater expertise and a bit more time than if you're doing something that uses basic methods or intermediate methods, because certainly you could use the AVERT model very quickly.
Actually, I did not say that.
So I guess I would, sorry?
Yeah, I did not say that. In fact, my advice is just the opposite. Start with the simple models. Work and get the simple models working. You start to add complexity, you better have a large bottle of Tylenol, because you might get staff up and running on it. They're here today, they're gone tomorrow.
Right,
Simple
great.
methods that are repeatable seem to work.
Yeah, great. Thank you. Yeah, it's exactly, depends on the purpose. So thanks so much for that, Jeff. Eric, did you have anything you wanted to add on that based on your experience in terms of how much time or how many staff you needed to do this type of analysis? Or David, any additional thoughts you wanted to add?
I'll just say quickly.
I have a few thoughts, but I'll let Eric jump in.
Okay, Eric, we'll start with you.
I was just going to say, there were a couple of us on the team that just ran various scenarios through the tool to make sure that it was really capturing the activities that we wanted it to capture for specific activities, like rooftop solar, larger grid scale projects, or energy efficiency. And then most of our time was not tweaking with the model or doing anything built off of it, but it was then regressing what factors we should use and then figuring out a way to operationalize it, which didn't take a huge amount of time.
Great, thanks. David, did you want to add to that?
Yeah, I guess I would just echo everybody's comments up to this point and say that, you know, the purpose of why you're using the tool has more of an impact on how long it's going to take you and how much you need to put into it than the tool that you actually use does. So the first study that I talked about, linking climate to and air conditioning to the health outcomes, that was like a 6 or 7 year project, you know, over $1 million budget. But the solar project, you know, we already had some data. You know, NREL invested a lot of money into that. On our end, it didn't take very long. I used an eGrid project that took me probably 3 months to write a report, and it was just me alone, so that's pretty cheap and easy. And same with Avert. I've done a very sophisticated analysis using Avert, and also simplified analysis using Avert. So it can be anywhere from months to years with any of those tools. And so picking the tool that fits the problem, I think is going to have a bigger impact on your budget and the expertise and personnel that you need than the tool itself, actually. And starting simple is definitely the way to go.
That's great. Okay, I like the starting simple message. David, while I have you speaking, I have a question that's targeting you. So essentially, I have a question here. It says, what was the future year that you were looking at on high and low SO2 emissions for the adaptation scenario?
Yeah, so the high and low, that actually comes from a different study that's published in ASHRAE by Scott Sheeter et al. And I don't actually remember what they did for high and low, but what we did for that study that carried all the way through, this was a separate thing that they did, was we looked at a series of regional climate model runs that are published in this big database called NARCAP, or the North American Regional Climate Change Assessment Project. And so they used a bunch of different model pairs to project climate out through the end of the century. And we picked a single year, and actually a single summer, from the mean model pair that represented the warmest year between 2050 and 2070 from an average model. And so the reason we did that, and I know this is getting complicated quickly, the reason we did that is we took basically the most realistic or the most trustworthy, or at least the most average performing model, and picked the warmest year in the middle of the century. So now this is a warm but expected summer in the middle of the century. So it ended up being 2069, but really it's just representative of the fact that we may have a warm summer in the middle of the century, and this is what it might look like.
Okay, great. Thanks, David. Okay, so I have, here's a question for Texas. The question asks, how did you determine emission reductions? Specifically, did you assume reductions from specific existing plants, or average reductions, or something else?
We did exactly per plant. Basically, our model go through the detail to go to per plant, the plants that are located in each county in Texas. So our emissions calculations are, as I was mentioned before, we have a model that go through from the main grid to in combination with a power generation. We were able to allocate in specific counties, depending on the real plant's production, what was the emissions that were produced, and from that we can forecast the emissions also attached to those plants that are in determined county.
Okay, great, thank you. Okay, I have a question for Eric, for the Green Bank. So what have you found in terms of, any results or impacts that you've found from having these program benefits that you've quantified through tools like Avert? So how has having this benefits information affected your ability to attract and deploy private capital investment, if at all?
I think I would love to be able to tell a story, and I think at some point in the near future we'll be able to tell the story I want to, that by highlighting the impact that we're doing, we're able to attract capital on more favorable terms than we would be without. But to now, we have not seen a pricing difference between the two, between having something rated and being able to talk about the impact. But I think that's more of a development of the market. However, with us going to access capital markets more and more, this being our first public bond transaction, it's more about us getting the habit of doing this so that we have a track record for it, so that as the market evolves, we're well established with describing to the market the impact that we're having. It also helps us on the policy front when we're working with our stakeholders, either from the regulatory perspective or from a legislative perspective here in the state, and saying, hey, here's a transaction that we've done, and this transaction, which is linked to this program that was mandated by statute, had this impact outside, assessed by a third party. So I think it helps us from that perspective.
Okay, great. Thanks, Eric. That's helpful. And I expect it'll evolve over time as people get used to and look forward to seeing the information in your report. I have a question for all speakers, and so hopefully folks can just take a few minutes because it could be a long answer, but hopefully you can just take a couple minutes to answer. But what did you find in the analysis that you described or in your experience doing this type of analysis? What have you found to be the biggest challenge, and then how did you overcome it? So let's start with, for Texas, how about we, in general, for this type of analysis, what do you find, or the analysis that you talked about, what do you find to be the biggest challenge? Or what did you find to be the biggest challenge, and then how did you go about overcoming it?
The biggest challenge are, or have been always to get the real and precise information. In the beginning of the project, that's what was a main issue, to try to even, for example, allocate the amount of energy produced in all the plants and every particular year and day and time, and try to get the correlated data with the outside and environment conditions. That was a big challenge to set it up, and it's still a big challenge. So for us in Texas, probably that was the main point that we have a problem for. After that, the challenges were mostly academic or scientific, if you wanted, to try to really get the real ways to model those, or to try to represent what really happened in every county. But that should be my point of view.
Okay. All right. Thanks. Eric, why don't I pass it to you? How about you talk about, through this process, what has been the biggest challenge that you've encountered, and how have you overcome it?
I mean, we're using the AVERT model in a very simple and straightforward way, so I wouldn't say that there were huge challenges in terms of implementing it and operationalizing it. I think we just had to work through and think through how we wanted to do that back when we adopted this model a couple of years ago. In terms of applying it to this, I mean, we're looking at 28,000 projects, so to run those through in groups in AVERT would have been, individually would have been fairly hard, so aggregating them and operationalizing it the way that we did made a lot of sense, and I think that was probably the biggest factor, although I don't think it was a severe impediment at all.
Okay, great. Thanks. That's helpful. David, how about you? What did you find to be the biggest challenge in either the analysis, either or both of the analyses that you talked about, and how did you overcome them?
Yeah, I think with the sophisticated tools, and this is actually already mentioned by Jeff and Juan Carlos, these big energy models are generally proprietary, and they're all developed for different purposes, even though they're fairly similar. Like I should have said, NEMS and JuiceBox are, they're fairly similar in what they're trying to do, but the meat of them is totally different, and it's because they were developed by different people at different places for different purposes, and neither of them, in general, most of the models are not cheap, or if they are, you have very limited access to them. So making them work with what you want them to do at a reasonable price is the biggest challenge.
Okay, great. Okay, I have let's see, we've got time for maybe one more question, and this is sort of just to anyone, and I know who might have the answer to this one, so you can let me know or let us know. Has anyone analyzed the technical potential air quality improvements from replacing all fossil fuel heat with heat pumps? Has anybody, give me a yes or a no, has anybody done that that's on the panel?
Not in Texas.
Not in Texas?
We haven't.
No, not here either.
We haven't, but it's something we could consider doing depending on what we're seeing in terms of growth in the heat pump market locally.
Okay. And that's David?
That was Eric.
Oh, I'm sorry, it's Eric. Okay, so that's something that perhaps Connecticut Green Bank might be a good one to look to in the future. Great. Okay. And then maybe one time for one more quick question, just for a suggestion. This, again, is for all speakers. What would be the best model to estimate the impact of changes to fleets from electrification? Do the models take into account more demand due to fleet electrification? So I know nobody here spoke about electric vehicles or changes to fleets. We've really talked specifically about energy efficiency and renewable energy resources that are, stationary source related. But does anybody have any suggestions for the best model to estimate the impact of changes due to electrification? Because of course there you'd want to take into account both the mobile as well as the stationary emission changes.
Yeah, I can speak to some of that.
Okay.
So to begin with, from the electricity side, any of these methods could work. You could use eGrid emissions factors. You could use AVERT and just change the demand profiles. Or, it's very similar to the work that we did where they were added electricity, or they were added demand for air conditioning, except in this case it's added electricity demand for electric vehicles. On the vehicle side, the best tool to use is a model called MOVES, Smoke Moves. It's an EPA tool for mobile vehicle emissions.
Okay, great. All right, thank you so much. Well, that gives us, that pretty much takes us to the end of the webinar. So I'd like to thank the presenters. I'd like to thank Jeff and Juan Carlos and Eric and David for your very interesting and informative presentations, as well as the answers that you gave to the questions at the end here. We will be making a recording available of this webinar, as well as posting the slides and a written transcript of the webinar. We encourage you, there is a webinar feedback form that you're going to see as you exit the webinar, so please take that webinar or give us feedback so that we can improve and enhance the way that we deliver these webinars to you. At the bottom here you can see that you can sign up for our newsletter on the slide that's posted there. You can join our LinkedIn group. You can visit our website. We will also be having, David mentioned this, we will be having another webinar. This is the first in a three-part webinar series. This one's on quantifying electricity and emissions benefits. We have another webinar coming up on May 16th that will be on quantifying the health benefits of energy efficiency and renewable energy. And then we're planning one to follow that on quantifying the economic benefits of energy efficiency and renewable energy. So with that, I'd like to thank everybody for their time, and I will turn it back over to the operator to formally close out the webinar.
This concludes today's conference call.